Hey guys, today we're going to do the final video on bipolar transistors, and in this video we're going to have a look to see what goes wrong with them, how and why they fail, and we're also going to look at how to test them, methods of testing both in circuit and out of circuit. So the first thing we need to say about bipolar transistors is they're actually very reliable devices. As long as it's used within the specification of the manufacturer, so the current and voltages are within the specified range, then there's no real reason why a transistor should fail. They don't have a shelf life as such. Certainly transistors you see these days don't have a shelf life after which they have expired, and they don't have a service life, where you can say, oh, transistors get old and fail after a certain period of time, in the way, for example, the electrolytic capacitors do that, but transistors don't. So basically, if you see a faulty transistor, there are a number of different possibilities that you're seeing of the fault. There are a number of different types of fault. The main ones are short circuit, fairly obvious. So the transistor has gone short circuit. Now, a transistor will draw an NPN one. Okay, transistor has three legs: collector, emitter, base. Now, a transistor can be short circuit between any combination of these legs. So you can have a transistor that is completely short circuit, base collector, base emitter, everything short circuit. You can have a short circuit just between the base and collector, or just between the base and emitter. And you can actually have a short circuit between the collector and emitter, but not to the base. Now, if you watch the first video about transistors, you might think that's a bit odd, because a transistor is made up like this with three layers of silicon, and this is an NPN, so you've got N-type silicon, P-type, and N-type, This is your base, emitter, collector. And you might think, well, how can it go short circuit between the collector and the emitter if it isn't also short circuit to the base? What can happen? A transistor can actually fail if there's too much current between the collector and the emitter, where effectively it blows a hole through the base. So your base, imagine this is circular now. Your base now looks like a donut, with a hole in the middle, and you can get sort of like metallized silicon, if you like, a whisker of metallized silicon that's gone through the hole. So now imagine your base is like a donut and the silicon's blown. I can't hold the pen and show you, but you get the idea, like that. So you can actually have a situation where the collector emitter is short and not to the base. The other common thing, as you can imagine, is open circuit. So the transistor's got open circuit. This basically would mean that there's no connector between the base and there's no connection between the base and collector, or the base and the emitter. It can't really go open circuit collector to emitter, because effectively that's an open circuit anyway when the transistor's turned off. So with an open circuit, it's either base to emitter or base to collector. You could kind of have an open circuit the other way, and I'll come to that, but it's not an open circuit. So short circuit can be anywhere: base emitter, base collector, collector emitter, collector emitter, base. Can be all of them. That's two things that can go wrong with transistors. The reason for these sort of failures would generally be because of some abnormal circuit condition. So for instance, a transistor is driving a load, and the load has become short circuit, and therefore the transistor passes too much current and it blows, it goes short. Same with open circuit, generally tends to occur with incorrect voltages. For example, the voltage between the base and the emitter should be no more than 0.7 volts. If that voltage for any reason goes above 0.7, again because some failing in the circuit, then the base emitter will go open circuit or possibly short circuit, but it'll blow, yeah. So that's the reason why. This brings us a couple of interesting things. Often if you find a faulty transistor, it's because of some other underlying fault, yeah, and you need to check the underlying fault first. I'll give you an example of this. Let's say you have transistor, yeah, load, ground, yeah, and a bias network that turns the transistor on, yeah. So this is plus volts, and this is your bias network. It's a resistor voltage divider, yeah, and it sets the correct voltage on here to bias the transistor, so it's just on, or however you want it to be, yeah. If this resistor here goes open circuit, then the voltage on the base will go up, and depending on the value of this, the current that's flowing, it's very likely that this transistor will go open circuit between the base and the emitter because the voltage on the base is too high. Yeah, that's fairly obvious. Now, what you can have is an interesting situation with this. Imagine this is feeding some sort of load, yeah. So this is your load, yeah, and the load goes short. Yeah, it's driving a speaker and somebody accidentally connects the wires together and short circuits the speaker. So this transistor goes bang, yeah, and goes short circuit, or it goes short circuit from the collector to the base. If it goes short circuit from the collector to the base, all the current flowing through the load, which is short, flowing through here, which is short, is going to flow through this resistor. So what it's going to do is it's going to burn out this resistor. Yeah, that resistor is now burnt out. It may be visible, it may not be visible. But one moment. Sorry about the phone call there. Okay, yeah, so if this goes short here, it can burn this resistor out, and you may not notice that. It might be visible, it might not. So you come along and find I've got short circuit load, yeah, you realise the load's short circuit, so you fix that, and you realise the transistor's short circuit, so you stick a new one in, and you switch it on, and it goes bang, or rather, it goes short circuit or open circuit base emitter. And the reason being, because you didn't spot that. So this is one of the things, if you see short circuit transistor, open circuit transistor, it's also worth checking if there's a resistor from base to emitter and there's a resistor faulty, yeah? So that's another thing. Okay, I mean there's plenty of other ways it can fail. There can be a resistor down here which can also go open circuit due to the surge of current down here. So I think you come to realise now that when you have a faulty transistor, you often need to have a look around to see what the cause of the problem was. There's other ways that transistors can fail though. One is called thermal runaway, yeah. This is not a way of failing as much as a method of failure. When you have a transistor in a circuit, okay, like so, yeah, and we've got a bias voltage on here, put the bias voltage in, yeah, and we've got a signal coming in here, okay, out, right. Basically, the amplitude of the out voltage and the current flowing through the transistor is dependent on the current flowing through the base, yeah, you know this. So a small current through the base puts a current through here, yeah. The current flowing through the transistor will cause it to warm up. Now the transistor has a property called gain, HFE as a symbol, yeah. So let's say we'll start off, there's 1 milliamp flowing through here and HFE is 100, yeah. So flowing through here is 100 milliamps. Okay. That transistor will start to warm up, and as it warms up, the base current stays the same, but the gain increases. So for every few degrees centigrade, the gain increases. So it might go from 100 up to, say, imagine it's at 100 degrees centigrade, yeah. So this might be, let's say this is at 0 degrees centigrade, yeah. By the time it reaches 100 degrees centigrade, put all degree signs in, yeah, the gain might be 2 or 3 times what it was at naught. It might be 250. Yeah. So this is where thermal runaway comes in. You've got current flowing into the base and 100 milliamps flowing through here, but the transistor's warming up. So the gain increases to 105. Yeah? Because the gain's increased, that means now the current coming through here has gone up to 105 milliamps. Yeah? And current causes heat, so the transistor heats up more. And because it heats up more, the gain goes up to 110, so the current goes up to 110. Yeah? And you can see where this is going, can't you? 110 milliamps flowing through the transistor generates more heat, so it heats up more. So you get this thermal runaway. It rapidly gets more and more current and more temperature till the transistor fails, goes open circuit or short circuit. This, obviously, when the circuit was designed, it was designed not to do this. But you can have a situation where, for instance, like a transistor's on a heat sink and it's come away from the heat sink a little bit, so it's not sinking the heat properly, and then you could get thermal runaway. So in this case, really, the transistor committed suicide, Harry Carey, yeah? Death by immolation, self-immolation. It burnt itself out. So that's a situation. It's an interesting one. As a repairer, you don't really need to know about it apart from just make sure if a transistor's on onto a heat sink, make sure you put heat sink compound on and make sure that it's firmly bolted to it. Yeah. Otherwise, it could fail again. So that's another way. Now then, how else can a transistor fail? It can become noisy. This is basically where, due to like an internal connection, and it's making and breaking, or something internal's happening, and you get a signal coming in here, which is a nice signal, but the signal coming out is all noisy. Yeah, you can get that sort of failure on a transistor. Another one you can get is low gain, where the transistor works. Yeah, it works. It's not open. It's not short. It works, but the gain should be, for instance, 100, and it's 4. Yeah, so effectively, it's just lost its gain. It's no longer working very well as a transistor. I think that's really the main likely cases you'll see with faulty transistors. Those are the ones I would keep in mind. Okay, so now we know what goes wrong with transistors. Let's have a look at how we test them, and we'll start off by testing them out of circuit. Okay. I will just mention, by the way, before we turn the page, I often have another thought. Transistors, when they fail, there's 2 other things you really should know about. Quite often, when a transistor fails, it can do it quite spectacularly. They can set on fire, they can explode, they can literally just detonate, yeah? They can set on fire, and often you can see, especially on large power transistors, a chunk missing out of it. So they can fail quite visibly and quite spectacularly. Another thing with transistors, you'll often have a circuit something like this. So we've got transistor, well, let's put a resistance in the emitter this time, it needs one somewhere. And this is connected with a bias, and it's connecting to another transistor. Yeah, I'll put resistor. It needs a resistor somewhere, and this is connecting to some sort of controller. Yeah, a microcontroller, something like that. Some sort of can I even write it? Controller. Yeah, control IC. And this control IC effectively is switching the circuit on or off, or whatever it's doing with the circuit. Yeah, out. Needs a resistor now, doesn't it? Because I've put an out. Can't have an out there without a resistor, mate. Okay. What I'm trying to point out though is this: if this transistor goes short circuit from collector emitter, say this is 12 volts up here, yeah, and this obviously is biased to have like 0.6 volts on here when the transistor's turned on. If this goes short circuit this way, the 12 volts will come right through into the base, yeah, and it can go into this transistor as well. And depending on the configuration of the circuit, this one going short circuit can cause this one to go short circuit. Yeah, this might say now be pushing too much current that way because that's all short, and this one blows short circuit. And then this one can now, because it's short circuit here, there's 12 volts coming down to your control IC, and that can go short circuit. So this is what I call it a cascade failure. This is a bit like this I was mentioning with burnt out bias resistors when you had a short circuit transistor. This is where you can have a fault that goes back through 3 or 4 stages of transistors and maybe back to the controller as well, yeah? So it's quite often you'll find that a whole on an amplifier channel, for instance, when the output goes short, you might find that almost every other transistor to the input's short as well, or open or damaged in some way. So that's another thing, yeah, with transistors. So now we will turn over the page and we'll look at testing. How do you test for faulty transistors? Testing. Right. There's a few ways we can test for transistors. One of them is out of circuit. Yeah. So when you've got the transistor out of circuit, yeah. And in this case, we can use a multimeter to do some basic tests on the transistor. Certainly will tell you if it's open or short, anything like that. We can use some multimeters have a transistor tester built in that basically measures the gain of the transistor. So if a transistor's got gain, it's probably working, yeah, and we can see what the gain is. This is my sort of main multimeter, my old Fluke, which I use all the time. This doesn't have a transistor tester built in, yeah, but this cheap one does down here, yeah, and we can use this to test transistors. I'll show you how to do it when we actually start playing with some transistors, yeah. That's 2 ways we can test. The other one is with a semiconductor analyzer. This is one of these, and there's a few different varieties and makes of these, and again I'll show you this. We'll use this to test some transistors, yeah. So that's the 3rd way we can test them out of circuit. In circuit, we can again use a multimeter, yeah, to measure voltages. This will give us a good indication if a transistor circuit is working or not, yeah. Also in circuits, we can use heat and cold. You'll sometimes find transistors that fail when they're hot or when they're cold, or a piece of equipment works and then it warms up and it stops working, or vice versa. And using heat from a heat gun or a hair dryer or something like that, you don't need a lot of heat, or your hot air station turned down to sort of like 60-70 degrees or 100. And using freezer spray as quite a common one for use to cool areas of a circuit. This can sometimes help you find transistors that are intermittent, yeah. So heat and cold. In fact, it's all heat. It's just the amount of heat or the amount not of heat, yeah. The positive or negative application of heat, yeah. Okay. Another way you can test them in circuit is effectively vibration. Just tapping on one sometimes will cause problems. It's another troubleshooting method. But really, those are the main ways you can test the transistor in circuit. The other ways to test a transistor is substitution. So you think you've got a suspect transistor, put another one in of the same type or an equivalent type, yeah? Put another one in, substitute it, swap it, see if the fault goes away or not. So that's really the ways of testing transistors both in circuit and out of circuit. So what we're going to look at first now is how to use a multimeter, yeah? This one, out of circuit. And then we'll also look at these. So I'll zoom the bench camera down a little bit and let's play with some transistors. Okay, so let's have a look at how to test transistors out of circuit, yeah? What does a transistor look like to your multimeter? Well, let's draw the transistor, yeah? Base collector emitter. Base collector emitter. This is an NPN, and let's have a PNP as well, yeah? So the arrow points the other way. So PNP transistor, NP, 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 yeah, base, collector, emitter. A transistor, as you'll know if you watch other videos, is made of 3 layers of silicon, yeah, doped silicon. So on an NPN, this is N type, this is P type, and this is N type, and this is the base, yeah, collector emitter. Okay. And on a PNP transistor, same but different. This is P, this is N, this is P, again base, collector, emitter. So in here we have 2 diode junctions. From the base there's 2 diode junctions. One is this junction, N to P type to the collector, and the other is this diode junction, yeah, to the emitter. And the same on your NPN, just the opposite polarity, yeah. And if you've watched the video on diodes, hope you did, or you'll know this. If we take a meter, yeah, and we put the meter onto diode mode, yeah. So this is now in diode test mode, yeah. Diode test mode. All multimeters near enough will have a diode test mode. If yours doesn't have one, get yourself a multimeter that does have diode test, because it's very important. And this doesn't measure resistance, it measures the voltage dropped across the diode junction. And if you watch the other videos on transistors, you'll know that for a transistor to turn on, there has to be about 0.6 voltage drop. In this case, NPN, the base is positive, about 0.6, and on PNP it's negative with respect to the emitter by about 0.6. And here we have a diode, yeah? So what this meter does in diode test mode, it measures the voltage drop. So if I go positive onto the anode, look there, you see the voltage drop, 0.569 of a volt, yeah? Okay, that's the voltage drop. And across the diode the other way, it's now reverse biased, so nothing will flow. When it's forward biased, it's not short, it has a voltage drop, 0.56, yeah? So this NPN transistor to your multimeter looks like 2 diodes like this. Yeah? It looks like 2 diodes. The anodes are both connected together, and there's the cathode of each one, yeah? So from the base is the junction of the 2 diodes. Although it looks like this on your multimeter, I must add you cannot make a transistor out of 2 diodes, okay? You can't make a transistor out of that. But this is what it looks like to your multimeter. So, as we just did with the one diode, if we put the positive on the base, yeah, we hold it still so it doesn't flick around. We put the positive onto the base. If I put the negative onto the emitter, I'll see a voltage drop. Collector, a voltage drop, yeah? If I now reverse it, so I put the negative on the base, I don't see anything. The diode is reverse biased, yeah? And likewise, if I go from the collector to the emitter across the 2 diodes, it's open circuit. Yeah, I don't see anything. Okay? So that's how it looks to your meter. It looks just like this. Base, yeah. Diode, collector, emitter. Yeah, that's what your meter sees. Now, you've probably already figured this out. A PNP transistor looks the other way. It's the same, but the other way around. So the diodes are now pointing in the opposite direction. So now we have base, yeah. We have diode like this, and we have diode like this, yeah. Collector, base, emitter. Because the diodes are the opposite way around, we now have to put the negative on the base to make it conduct, yeah. So negative to the base, collector, collector, yeah, we see the voltage drop. Emitter, we see the voltage drop. The other way around, we'll see nothing. Yeah. And between the collector and the emitter, we'll see nothing. Collector, emitter, yeah, no matter which way around, collector, emitter, you're going to see nothing, yeah. So, with a multimeter, we can easily test the junctions are there. Doesn't necessarily mean the transistor's working, but the junctions are there. It's not short circuit or open circuit between the base collector or the collector emitter. We can also check that it isn't short circuit from the collector to the emitter, yeah? But not only can we do that, we can actually tell whether that transistor is NPN or PNP. Base P, yeah? So if it's an NPN and the P positive is on the base and it conducts, that's NPN, yeah? PNP, N is the base, the middle one, and it conducts that way. So if it's a negative on the base, it's a PNP. If it's a positive on the base, it's an NPN. So you can also tell that with the multimeter as well. So that's what the actually transistor looks like. So now let's actually have a look at some real transistors, yeah, and see what we can determine what they are. Okay, so do we need a new piece of paper? No, we don't need a new piece of paper. We just need to zoom the camera down a little bit more. Okay, so here we have two general purpose transistors, yeah? This one, I can look at the part number, you probably won't see it on the camera, but this one is 2SB621, marked B621, you can see it, yeah? So that is a B621, which will be a 2SB621. You should be able to find the data sheet either way. I've written it here, yeah. But that's what that transistor is. Now the other one, this one is a BC337. You might just see that on there. I'll just catch the light on it, right? Yeah. This one is a BC337. So that's the two transistors we have. Now, can we determine if the transistor is any good using the multimeter? And can we also determine which pin's which, yeah? So let's use the B621 first. I've put the meter here where you can see it. So we don't know which pin's which at the moment, so we need to find the base, yeah? We need to find the base, if it's a good transistor. Well, let's assume it's a good one for now. So we'll put the positive on the pin at this end, yeah? Just by random, I've now got the positive on this pin, yeah? We're going to put the negative on the middle one. There's nothing there, yeah? We go to this end one. We have something. So one of these two is the base, yeah? But because there was nothing there and there was nothing there, sorry, there was something there. What's the connection? Yeah, got it. Okay. The chances are this one's the base, not this one. Because if this one's the base, you expect to see something on both of them, yeah? So the chances are this is the base, yeah? If this is the base, then this will be one of the other pins in the middle, yeah? And it is. So from this left-hand one, we've got a connection to the other two with a diode junction. And this left-hand one is negative, yeah? Negative. Yeah, PNP, N is the base, negative, yeah. So this almost certainly is a PNP transistor, yeah. The last thing we need to check, so we know this is the base, so we know we've got a good diode junction to the other two, is between the collector and the emitter. So one of these will be the collector, one will be the emitter, yeah. There should be nothing either way. There was nothing there. There's nothing there. Okay, so we know it's a PNP and we know this is the base, yeah? So we can draw our little transistor. Here it is, with the flat side towards us. There's three legs, yeah, and we know this one's the base. Okay, can we work out which is the collector and the emitter? Yeah, you can. Not absolutely 100%. You might find this fail occasionally, but generally speaking, you can. Let's have a look at these forward voltage drops. So from the base to the middle pin, 0.609. Let's try this one. 0.613. Yeah. So one is a little bit higher than the other. Yeah. 608, 612. The one that's a little bit higher is the emitter. So this is the emitter and this will be the collector. And that almost always works. And before somebody jumps on me, yeah, I know, just occasionally it doesn't, yeah. But almost always that is correct, yeah. So whichever one's the higher of the forward voltage drops is the emitter, yeah. Let's look at this other transistor. This is our BC337, yeah. This is this one, BC337. So we've identified that one. Let's have a look at this one. So again, we'll start with the positive. We'll start with the positive on this end, and we'll see: do we have a connection to either of the other two pins? No. No. Okay. So we don't know anything. So let's put the negative on this end now. So we've tried the positive on it. Let's try the negative on this end. And it doesn't matter what order you do this in, by the way, whatever suits your way of thinking better. But I'm going to put the negative on, yeah? No. Ah, now I have something, yeah? With a plus in the middle. If this was the base, you'd expect it to be an NPN transistor and connect both of them, but it doesn't. So the chances are the middle one is the base. And it's an NPN, because I'm on the positive lead, yeah, in the base. So am I expecting now to see a diode junction? Yes. Yes. So, yeah, we'll draw a little picture of it. That's the curve. This is the flat side, yeah. They have like the curve, they have a flat side, yeah. And we know it's NPN, and we know this is the base. NPN, yeah. Let's make sure the collector emitter, there should be nothing because it shouldn't be short, yeah, or no leakage. Did I mention leakage? That's another way transistors can fail. They can go leaky. I forgot to mention that one. Transistors can go leaky, so that when they're turned off, they're not fully turned off, yeah. Imagine that thing with the water pipe where we have a control narrow pipe and a big pipe if you watch the earlier video, otherwise you haven't got a clue what I'm talking about. Imagine the big disc that closes off the main supply. It's got a rubber seal and the rubber's worn, yeah, so it leaks. Same thing happened with the transistor. Okay, so there's no leakage on this one. We know it's NPN, and we know the base is in the middle. Again, can we find the emitter? Hold this on there. And let's see again what we got. So to this end, 648, 649, 647. Not a lot of a difference, but one is slightly higher than the other, and the one that's slightly higher than the other should be the emitter. Just check him again. 648. You see I've shorted the legs together with the meter there. 647, 649. So very little difference, but it's looking like this one's the emitter and this one's the collector. Yeah. So we've identified some transistors there. Shall we see if we're correct? Let's go on the internet here. Let's go on the internet and have a look. So we have a B621, which is probably a 2S B621, and we have a BC337. Let's go on the internet and see what we can find. Close this one. Okay. We can just search if we want for like BC337 datasheet, yeah? And you'll find the datasheet if we look at that, yeah? All datasheets, we use that one a lot. But with transistors, there's another site I want to show you, yeah? And it's called All Transistor. You could look up the datasheet, the other one, but we go to All Transistors, alltransistors.com. Now I want to show you this website. So in here, we'll search for our transistor, BC337, yeah? Let's see if we can find it. Yeah, it's found them. It's bipolar junction transistor. And it's found lots. Let's just see if it just says BC337 like with nothing else, yeah? Only problem with this website is the stupid adverts that pop up. And then half the time don't want to disappear again. There it goes. So this is our transistor, BC337. Yeah, it's a silicon transistor, NPN. I mentioned, by the way, there are other types of transistors. There's germanium as well, but they're so old you won't really see them unless you're working on vintage equipment. Yeah, but you can get germanium transistors, NPN and PNP, and the main difference is they have a 0.2 volts forward bias on the base and not 0.6 or 0.7. Chances are you'll never see one. I don't have any here. I gave all mine away to a guy who worked on vintage radio amateur equipment. I had loads of them. I just give them to him. I don't need them. Okay, so this is the data sheet, yeah? And it's legs 1, 2, 3, yeah? And it should tell us, yes, 1 is collector, 2 is base, 3 is emitter. I'll write that down on my little sheet, BC337. So 1 is collector, 2 is base, and 3 is emitter, yeah? And this gives a specification for it. But before we got to that, here it was also giving us the information we need, yeah? And then much easier to read form. That's why I like this website. And then we have this equivalent substitute. This allows us to find an equivalent transistor if we haven't got a BC337. It's filled all this information in for us. You can fill this in manually for a transistor that isn't in the database if you have the information. Yeah, and look, it gives you here many transistors that are equivalent. Yeah, many. So this is a useful site if you want to find equivalent for an exotic transistor. I mean, BC337 is a very common one. So that's why I wanted to show you this website in particular. Let's now have a look for the other one, which was the B621. See if we'll find that. B621. Look, it's come up 2SB621. It knew it's that, yeah? So we'll go with it, 2SB621. Again, it's a silicon, it's a PNP, that's what we thought it was. Here's the various specifications. Again, we could find an equivalent for it if we so want to. This is the data sheet. And we can see the legs again, if you just zoom in a little bit. So we can see 1, 2, 3. Can I move this sideways? I have to scroll it. Okay, so 1 is emitter, 2 is collector, and 3 is base. Yeah, 1, 2, 3. Emitter, collector, base. And it's showing you with a flat side there, yeah. I tried pointing at the screen then. Show you with a flat side there so we know which one is. So it's emitter, collector, base, 1, 2, 3. This might be quite an unusual transistor. Let's see if we can find some common equivalents to this one, yeah. Again, it's filled the information in for us. Look, and it's given us loads and loads and loads. And there's some BC ones that might be easy to find, yeah. BC488, BC527, which I think is quite a common one again. So yeah, so this is a very useful site. Make a note of that, guys. Alltransistor.com. I'll write on my bit of paper, yeah. Alltransistors.com. Okay, so let's go back to our transistors and see if we were right with the pins we identified. There we are. And I wrote the numbers down, yeah? And they're exactly as we drew them. One was emitter, collector and base on the B621. And on the other one, the BC337, collector, base, emitter. So we identified them correctly, yeah? But you notice on this one, it was very close. It was very close. It was like, 0.002 voltage difference between the base collector and base emitter. Okay, so can we test these transistors a little bit more? Yeah, we can test them with the multimeter as a built-in transistor tester. Now we know the pin outs. Let's zoom the camera back out and let's test them that way as well. Okay, so this is the multimeter that has a built-in transistor tester. So there's a little socket here, yeah, and it's marked base emitter, base collector here, yeah, in uppercase and then lowercase BCE, yeah. And this is saying NPN and this side's PNP. So our BC337, we know it's a PNP transistor, and we know from the data sheet which pin is which, yeah. And this socket's designed that no matter which the pinout is, by putting it in the right position, the right way round, you will always get, get it oriented to test it. Yeah. So in this case, this one is the emitter. Yeah. And down here it says E, C, B. So we'll turn it back to front like so. We'll set the meter to gain, yeah, HFE, and this will measure the gain of the transistor. 188, yeah. I lost the connection. It's a bit of a dodgy connection on this meter with the transistor. 187. So we know the transistor's working and we know it has gain. We don't actually know if the gain's correct, but we can go to the data sheet and look for the minimum, maximum, typical gain and decide if that transistor is actually correct, yeah? Let's have a look at the other one, the NPN one. So this is collector at this end, yeah? Base in the middle. And it's on the lower case, so we want collector this end, base in the middle. So it goes like so. Collector, base, emitter. Definitely the right way round. No, I'm wrong. I went collector, emitter. Collector, base, emitter. It's up here. Again, with the flat side, this is the collector at this end, base in the middle. So you see, if you put it in the wrong place, it don't work. Yeah. Don't mean you got a faulty transistor. Just means you didn't put it in the right way round. User error. 262. Yeah, so that's got a good gain. The chances are, for a signal transistor, if it's like in the range of 50 up to about 400, it's probably okay. But again, you could use the data sheet. So we can use this meter to test the gain of a transistor. That's a handy little feature. Is it worth buying one if you don't already have one? No, but buy something else. I'll show you. But if you do have it, it's useful. It's useful. Okay, so let's look at some more transistors. We looked at those two. We've identified them. Let's have a look at some more. Let's look at some power transistors. This one's TIP42C. If you'll see the number, let me see if I get the angle. Let me do it the other way, because you'll want to see it, won't you? This is the right one. I would, but the torches fell off where it normally lives. But that's it. It's a TIP42C. Power transistors, usually this end is the base. Usually, yeah. Let's have a look. Nothing there. Nothing there. But I expect this probably is the base. Let's reverse the polarity. Got it. Voltage drop. Voltage drop. So this is the base. Yeah. The collector is normally in the middle, and as well as go to this pin, you can normally go to this tab. It's the same thing. Yeah, the tab and the leg are connected together. 587. 588. Extremely close, but this is the collector. This is be the emitter. Yeah. So that's a good transistor, in as much as it's not short, it's not open. Yeah. So let's put that on the good pile. Yeah. No. So I've got another one. What's this one? This is a it's got numbers on it. Even I can't read this one. No, I can't easily read that one. Let's have a look at what it is, yeah? Nothing there, nothing there. I'm thinking this is probably the base, and this is probably a PMP. Nothing there, nothing there. What about between the other two? Nothing there, nothing there. Positive in the middle. Oh, I've got something here. Right, so in this case, this is the base, yeah, this end. It's a PNP because I've got the negative on the base. 639. What did I have on that one? Ah, see now this one, I told you it wasn't 100%. This one reads 639. Down to is it 639, 639. So our mysterious device here We know it's for PNP. It reads like a PNP transistor. This is the base, and we don't know which of the collector and the emitter are. So let's put that one on top. But it looks like a good transistor, but we don't know exactly what it is. Let's have a look at some of these. These are MJE3055. They're both the same device, MJE3055. Let's see what these look like. Again, most likely this side's going to be the base. Nothing there, nothing there, nothing there. Let's go the other way around. Nothing there. Ah, okay. That's forward. So again, this end appears to be the base, not this end. 515, 520. So base collector emitter. Yeah. On a power transistor, almost always the collector's in the middle anyway. Almost always, yeah. 515, 520. So this one we seem to have base collector emitter, and it appears to be a good transistor, yeah. So look at this one. Now we know which way around it is. Yeah. 573, 519, 513 was it? 513, 519, and nothing between the other two, and nothing with the negative on here. Yeah. Because it's working when the positive on the base. These are NPN. So we've got a couple of NPN transistors here, yeah? They're NPN. So look, just a few more. These are big power transistors. These are TIP33C. Yeah, TIP33C. So look at these. Again, we'll start on the assumption that this end's the base. Yeah, this end. It might not be. One on the base. Collector. Ah, that's a short circuit. That's a short circuit. That transistor is short circuit everywhere. Base, collector, emitter. That's a lump of metal. That's no longer a transistor. That's a lump of metal. That's a bad one. So look at this one. Nothing there. There's no short on this one. Let's go with a positive on here. In case this is the base, it's an NPN. Yeah, got a junction there. Got a junction there. Which way round is it? 570, 572. Almost certainly this is the collector in the middle anyway. And that's what we have, base collector emitter, and nothing between the other legs or the other polarity. So that was like a good transistor, yeah? A couple more, see what these. Let's look at the rest of them. There's another short circuit transistor. Yeah? That's a bad one. Last one, what's this one like? We know now we think it's base collector emitter, so I can go straight away the right way around. That looks like a good transistor. So it looks here, all in all, we have 8 good transistors. These we use the transistor tester on the multimeter. We can even measure the gain, yeah? These we know they're not open or short. We don't know if they're working, but we know they're not open or short. These we know they're working, yeah? So, can we use the transistor tester? Can you get them legs in them holes? You could make some wires with little clips. You could do it, yeah. You could get some, stiff wire that sticks in the holes and put little clips on the other end. You could do that if you wanted. I wouldn't bother. This is a semiconductor analyzer. And I'm going to use this. So let's look at these 8 transistors on the analyzer, yeah? And the good thing with this analyzer, put it into view, yeah, good thing with this analyzer is you don't actually need to know which is the base collector and emitter. You don't need to work it out because it will tell you. And you can just connect the transistor up however you want, doesn't matter. Okay? Just connect it up, switch it on, see what it does. NPN silicon transistor. NPN silicon transistor. It tells us which colour the wire, so it tells us the base collector emitter, which if you look at the green, red, blue is exactly how we worked it out. So we were right, yeah? It'll tell us the gain, 245. I think we've got a similar reading on the test meter. That's just the test current, not really important. And that's the forward voltage drop between the base emitter, 0.72, to turn the transistor fully on. Yeah, and that's just how it's using 4.6 milliamp test current, and there's no leakage. Yeah, so that's a good transistor. So have the other one, little one. So this is the PMP one, this one here. So it should tell us green as emitter, red as collector, blue as base. Yeah, so that's the way I've connected these up, just by chance. PMP transistor, we knew that. Yeah. Collector, emitter, base. Yeah. Blue is the base, green is the emitter, red is the collector, so it matches. This one has a gain 174. Yeah, it read on the meter, a bit less than the other one. About that. Test current again, slightly lower forward voltage bias drop. No leakage. So that's a good transistor. This is our mysterious one. Yeah, that we couldn't really figure this out. We could figure out where the base was, but we didn't know where the other two were because it was the same. It looked like a good transistor. So the red is on the pin that looked like the base, unless I've turned this upside down now, of course. I don't think I did. Clip them all on, let's have a look at it. PMP transistor, yeah, we figured that out. Red is the base, yeah, we figured that. Right, now this tells us now the green is the emitter and the blue is collector. Which kind of makes sense. I said on a power transistor, normally the middle pin is the collector, yeah? So we now know about our mystery transistor. We haven't got many more to test, have we now? This TIP one. We managed to identify this anyway, so all this will tell us now is, does it have any gain? If it has no gain, it ain't working, yeah? PMP tells us the pins, does plenty gain. That's a good transistor, and it has no leakage current. That's a good transistor. Okay, get them off here. We've done the mysterious one. Let's have a look at these four. These two tested good, yeah. What we got? We think probably base, collector, emitter. This end might be the base actually. We'll soon remind ourselves which way around it was. Yeah. NPN transistor. So red's collector in the middle, blue is the base, yeah. Gain 136. Different, a bit lower voltage drop across the base emitter on this one. No leakage, that's a good one. 3 left, eh? Let's look at this one. Again, connect it the same way as the other one. NPN transistor. Again, blue is the base, green's the emitter, red is the collector. 76. That's a fair bit lower than the other one. I would say with these two, you would really need to go and look up the datasheet to see whether this one is within spec or not. Yeah, this might actually may be a bad transistor or one that considerably less gain than it should have, and that could cause this to not work in circuit. So you need to at least go and look that one up. Yeah, we'll try in a minute. 2 more. Hope I haven't bored you yet. It's quite therapeutic, this is actually just doing this. That's got a low gain 27, yeah. No leakage. It's not unusual for power transistors to have a low gain, but it's a bit strange that these are so different. So let's try this one. Gain of 20 on a power transistor isn't particularly necessarily something that's bad, but we'd expect them to be roughly the same. NPN transistor, yeah, 28. So the two are about the same. So I think we can say it's unlikely to have two transistors that are faulty with low gain and they're both the same, yeah? So they're good. So the only one we can say we're a bit suspicious about were these two. One had again, I think was 70 something. $77, and the other one it was 140 something. Remember what it was now. $137. So those ones, the MJE 3055, we need to look at. Also, these components analyzers, we'll have a look at that as well. This cost me about €60, or 60 quid, about 4 years ago. Yeah. So it wasn't the cheapest bit of a kit. You can see it's very useful, and it does more than just test transistors. It does MOSFETs and thyristors and all sorts of things it will automatically identify and test. Okay, so let's go back onto the internet and have a look to see what the rating for this other transistor should be. We'll stay in this all transistor, MJE3055. MJE3055, yeah, that one. Well, actually, it's saying that the minimum gain HFE is 200. The minimum, yeah. So maybe they're both okay, but this raises an interesting thing: is if there's more than one of those in the circuit, so they're working together, I would be suspicious of that, and I would tend to try to replace them so that all of them have the same sort of gain, especially in amplifier circuits and such like. Those two transistors will not work equally together. So if they're in a situation where effectively they're sharing the load, yeah, they're in parallel basically, I would certainly consider that would be a problem. Okay. While we're in here, let's have a look for these semiconductor analyzers, shall we? Let's go to AliExpress. Semiconductor analyzer. Okay. Oh, interesting. Well, there's lots of them here that seem to be quite cheap. Yeah. Is that a semiconductor? What's this? I mean, less than £20, so a lot less. Oh, you can buy the leads separately. You can buy it. Oh, there's an adapter for it. Yeah. See if there's any more. Yeah, they come with the various kits for the leads. Is there any like DIY kits? You know, like effectively, like you buy the bits and build your own. Power current analyzer. Sometimes spelt that way, the English way. Finding all sorts of strange things now. Let me have a look, because I'm pretty sure I have seen something else as well. One moment. Okay, I just paused the recording there where I actually logged into my account for obvious reasons. I just didn't want to be online when I was logging in. So yeah, there's this one. I'd found this before. It was in my wish list actually. Look at the price of these, like €4.70 plus shipping to Spain, €1.60. So you're looking at like, you know, €5.70, about just over €6. Yeah. About £5 in English, a little bit more in dollars, but it's less than 10. So you can get these things: digital transistor tester, meter, diode, triode, capacitance, ESR meter. It's an interesting bit of kit, isn't it? What do you think? I'll tell you what, guys, I'm going to buy one. I'm going to buy one of these. It'll take a few weeks to get to the Canary Islands because they send it by bloody turtle or something. Strap it to a turtle and send it swimming over, I think, for the amount of time it takes. I'll order one of these and let's try it. Let's do a video on it. If this works well at that price, it's something you should all have one of these. But let me try one first. If you want to have a go, just go grab one and let me know. Your post will be quicker than me. Automatically detects NPN and PNP, N-channel and P-channel MOSFETs, diodes, double diodes, thyristors, transistors, resistors, capacitors, and other components. It detects just about anything. Oh, yeah. Wide range of capacitors, ESR. Gotta have one of them, Gotta have one of them, guys. Let's order one. I'll get it on the way here, and then I'll review. Will review that. Yeah. Okay. So we've looked at how to test transistors out of circuit. Yeah. What we really need to do now is have a look to see how to test transistors in circuit. So let's start with another piece of paper. I mentioned you can test transistors in circuit using a multimeter. Yeah? And I mentioned you can measure voltages. You can also measure resistances or use diode test mode as well in circuit. And this will certainly spot short circuit transistors. It may not possibly always detect other problems. You may have to remove the transistor to have a look. But let's have a look on the circuit board. There's a circuit board, yeah? And first of all, let's have a look at resistances. So we're on diode mode, still on the meter. Shorting the leads together, just unravel them a bit. Why is it that over use your meter leads always tangle up, but they never untangle? Because like by random, you think like, well, you'll either twist them one way or the other. So you'll either add one twist or remove one twist. So you think they shouldn't, but they do. They always twist up after a period. Okay, here's a transistor. It's actually marked, if you can see on the circuit, CBE. Let me see if I can get a little bit closer on that. Are we on full magnification? Yeah, well, full magnification now. So this is a transistor. It's marked CBE, collector base emitter, so we know it's a transistor. On the board it's marked Q216. Q is commonly used for transistors. So if you see Q something or other, is often a transistor. In the old days it used to be T or TR. These days it seems to be Q. So depending if you work on vintage stuff, it might be different. Also, just because it says TR doesn't mean it's necessarily a bipolar transistor. It could be a MOSFET, yeah? Or if it says Q, it could be a MOSFET. Everything that's on three legs isn't always a transistor, yeah? On Surface Mount you can find diodes that have three legs, but they only use two of them. So this is our transistor. So let's see if we can test it, see if it's NPN or PNP, or if actually we think it's good. So we know where the base is, it's marked. So let's put the positive on the base, negative on the emitter. Well, it's reading something, but it's not reading the diode junction, yeah? That looks like a capacitor charged up, so there's nothing there. So across the collector emitter, is there a short? No, I can see a diode junction, but not a short. So negative on the base. That's the diode junction. So it looks like it's a PNP. 0.641. 0.640. Yeah, the emitter was slightly higher again, yeah. So it looks like it's a good transistor, apart from we see a diode junction across collector emitter. But without having a look to see what is in the circuit, what it's connected to, we don't know whether that's actually a problem, you know. This could be connected to another transistor driving it, so the collector drives the base of the other one. And if both emitters on ground, you would see a diode junction, yeah. So it looks like a good transistor. Unless we have some reason to suspect it, we'd probably say it was good, yeah. But otherwise, we have to take it out. Yeah. This is a Q. This is a Q something or other. Can't quite read the identification on this. It says HS2. That's the heatsink. Well, it's got three legs on it. It looks like it could be a power transistor. So let's just have a look. Let's assume this is the base. That's not a diode junction. capacitor charging. Let's go the other way. That looks like a diode junction. That looks like a diode junction, and collector emitter, nothing. So that, oh, we see, yeah, it's just a capacitor charging, that'll eventually go away. So that looks like a good transistor. It certainly ain't short, and it probably isn't open base collector base emitter either. There's a couple more over here. Let's have a look at these. So what we got on this one? Again, let's assume this is the base first. Yeah, we've got a diode junction. We've got a diode junction. That's considerably higher than this one. 485, 592. That's collector emitter, you would think. And you assume the collector's in the middle and attached to the heatsink, yeah? Watch out these heatsinks, they're connected to the collector. If there's a high voltage on that collector, and the fact there's a cutout in the circuit board here tells me there is a high voltage on that collector, there's a high voltage on the heatsink, yeah? Because it ain't insulated from it. Actually, no, it is insulated. No, I thought I had a connection there. That's strange, isn't it? No, I don't have a connection to that. I thought I did. Watch out for that. Sometimes heatsinks can be live, yeah? Another one. 493. 528. Reads like that one's probably the same sort of device. Not sure, yeah? When you have transistors near to coils, it's quite possible to reach what look like shorts and they ain't, yeah? So that's something to bear in mind. If it's near to a coil, you might read like a short circuit base emitter and it ain't. You're reading the coil. And obviously the coil is only a short effect, like DC at AC it isn't, yeah? So that's those ones. Let's have a look on the other side of the board. If you have power transistors, like the ones we just looked at, by the way, over here, yeah, so I can see where the legs come through. That's the heatsink. These are the legs here. I'm off the camera. I'm even more off camera. I'll be in a minute. I'm there. I'm on it. Okay. If you have a transistor like this type and it doesn't quite seem to read properly in circuit, a useful little trick, if we just put the soldering iron on, get a bit of flux and a bit of leaded solder, yeah? Find some leaded solder, a bit of solder braid. Solders around here somewhere. We use the thin stuff. I can't see I found the thick stuff. Another little trick we can do like this is like this. So if we're suspecting this transistor, yeah, and we have, maybe we can see a diode reading where it's not the transistor, we can actually often check these in circuit. So what we do is we stick some solder on each of the pins, yeah, bit of solder on each pin. We'll get the solder flux on there, so a bit of flux, yeah, a bit of braid. And we're going to desolder the transistor, but we're not going to remove it, we're just going to desolder at least 2 pins of it, yeah? It can be a little bit tricky. Let's see if we can actually desolder a couple of pins of this transistor. Yeah, looks like we've got them. Right, we can often desolder just 2 pins, yeah? And if we've actually got those pins free of the solder, let's just check. Do they move? That one moves. See if they move. Yeah, that one moves. That one moves. What you can do is, you can effectively break the connection. So now, on this transistor, from this pad should go to this pin. It's not connected anymore, yeah? And the same from this pad, not connected. And we can now test, yeah, between there and there. It doesn't matter this one's soldered, because this one isn't soldered. So now we will only see a diode junction there, and you shouldn't see anything between these two. As before, you might have measured the diode or resistors. Yeah? So that's a neat little trick, easily done with power transistors, if you want to be sure, yeah? And power transistors are the most likely ones to fail, so whatever's doing the most work is the most likely thing to give it up, yeah? Last thing, let's have a look around on the resistances, and let's find some surface mount. There's some surface mount transistors on here somewhere. Yeah, there's a little group of them here. Yeah, these little packages called small outline transistor 2-3, which is 2mm by 3mm, I think. SOT 23, yeah, 3-pin. These are often transistors. They're marked here as Q202, Q203, Q208. They probably are transistors, but they could be FETs, they could be transistors. You don't really know. Can we test these in a circuit? Yeah, it's the same as testing the other ones. So there we have nothing. There we have nothing. The middle one's usually the collector again. There we have a junction. And there we have a junction. So that looks like it's okay. We see a junction across the collector emitter both ways, one side and the other. So the only way to be sure of that transistor, if you suspect it, would be to take it out of the circuit, desolder it, test it and put it back. Yeah. You can easily clip your little component analyzer on these if you've bought one of them €5 things I'm going to buy. So that's how we can test them in circuit. Yeah. Sometimes it's inconclusive and you can't say for sure, but you'll certainly find short circuits this way. See, again, that reads both ways across there. So to be certain, you'd have to take it out. The chances are they're all so close together, they're probably all interconnected. Junction there, junction there. That means nothing across that one. That one just reads like a transistor. So that one we can say looks good. These two, yeah, maybe. But as I say, not everything on three legs is a transistor, yeah? And certainly not a bipolar transistor. Okay, so let's have a last thing to look at now is how to test transistors by measuring voltages. So finally we'll have a look at testing transistors in circuits using voltages, yeah? So, what voltages can we measure on the transistor? Well, the most important ones are the voltage between the base and the emitter and the voltage between the collector and the emitter. Yeah? There we have a circuit. When the transistor is turned on, so it's forward biased, yeah, the voltage between the base and the emitter is going to be around 0.6 volts. Yeah? But a 12 volt supply. So when the transistor is turned on, it's going to be about 0.6 volts for an NPN transistor, yeah? If it's any more than 0.6 volts, so if it's greater than 0.6 volts, 0.7 shall we say, yeah, then the transistor must be open circuit, yeah? Open circuit, base to emitter. It's got to be, because it can't be more than that across a working junction, semiconductor junction, yeah? So if it's more than that, it's got to be open circuit. If it's less than 0.7 volts, yeah, then there's two possibilities now. Either the transistor's turned off, yeah, it's off, or it's short circuit. Especially if it's near to zero in this instance, yeah, it's short circuit, base, emitter. Those are the two things, yeah. The voltage could be negative, yeah. That's fine. If it's negative, it's just very, very turned off, yeah, for an NPN transistor. So that's measuring the voltage with your meter probes from there to there, straight to the base emitter, not to ground, because there could easily be another resistor in here before ground, yeah. Measuring between the base and the emitter of the transistor, and you either expect it to see 0.7 volts if it's fully on, 0 volts or thereabouts if it's off. And if it's somewhere between 0.6 to 0.7, it could be in its active region, it's acting as an amplifier, yeah? Okay. The other voltage you can read on a transistor is the voltage between the emitter and the collector. Yeah? put your test meter here and here. Now, depending what you saw on the base, you'd expect to see one of two things. If the voltage on the base was less than 0.6, this transistor should be turned off. So if, for instance, like there was 20 volts here, yeah? If there was 20 volts here, and you go between the emitter and the collector, there you'd expect to see 20 volts. There's no voltage drop across this resistor because there's no current flowing, yeah? That's if the transistor is off, so there's 0 volts. If there's less than 0.6 volts on the base, yeah? That's what you'd expect to see. If there's more than 0.6 volts on the base, you'd expect this transistor to be turned on, yeah? So you'd expect the voltage here to be somewhere less than 20, yeah? If it's in its active phase, it could be anywhere between 20 and when it's fully turned on, it's about 0.2, yeah? Could be anywhere in between. If it's fully turned on, so there's like about 0.7 volts on here, expect this to be fully turned on and expect to find here 0.2 volts. Yeah, so that's with the emitter across the emitter and the collector, yeah, base. So really that's the two things you can check on a transistor, yeah. If this is 0.7 and this is still 20, the chances are the transistor's faulty. It's either open circuit here or open circuit here, because it should be turned on, it isn't, yeah? So really then, guys, this is the big moment now. This is where you can test yourselves and see how well you followed what was we've been talking about, and a little bit of this will tie into the previous sort of tutorials we've done as well. So hey, let's have a go. Let's have a little test and let's see how you deal with this. Yeah, what do you think? Okay, so we'll have a simple transistor circuit. We've got a 20 volt power supply, yeah, and we've got here a resistor, collector emitter, another resistor to 0 volts, yeah. This is an NPN transistor. Okay. On the base we have a resistor going up here to the 20 volts. We have another resistor going down to 0 volts, yeah, and these are the bias resistors, yeah. In here we have a capacitor, and this is the input coming from other part of the circuit where it's sending the signal in, yeah. From here it goes to the output. Now let's put some values on here. Say we've got a 80 kilo ohm resistor here, yeah, a 20 kilo ohm resistor here. This one's a 4K7 or 4,700 ohms, 4.7 kilo ohms. I'll put 4K7 because it's the shorter way, yeah. This is a 1K resistor here. Okay. So this is the circuit we have on the circuit board. And we take our test meter and we connect the negative probe to the ground, yeah. We connect the positive probe to here, the base, yeah, the junction of the two resistors, and we read 4 volts. Okay. Now we take our test meter again and we measure from ground again and we measure to the emitter, yeah. And here we're going to measure and we see 3.3 volts. We now take a test meter from here, ground, and we measure with our test meter again to the output, yeah, to the collector, and here we see 20 volts. And then again we take a test meter from here, and we measure to the power supply, and we see 20 volts. Right, is that transistor circuit working? And if it isn't working, what's the problem with it? What's wrong with it? Yeah. Right. Let's look at what we know. We know we have 4 volts here on the base. Yeah. We know we have 4 volts here, and we know this is a voltage divider, 2 resistors. Yeah. And without even doing any maths, we can work out what the voltage should be here, because across the whole lot, 100 kilo ohms is 20. Yeah. If you like, 80% of it is here and 20% of it is here, yeah? It's easy maths. 20% of the resistance is here, 80% is here. So 20% of the voltage will be here, and 80% will be here. So the voltage between the base and the ground we'd expect to be 4 volts. Yeah? About 20% of that. And the other 16 volts, if you're wondering where it is, it's there. If you put your test meter across that resistor, yeah? So 4 volts is very reasonable. We've now measured from ground to the emitter, yeah? Base, collector, emitter. And on the emitter we can see 3.3 volts. So we know the voltage between the base emitter is the 4 minus the 3.3. So the forward bias, base to emitter, must be around 0.7 volts. Yeah? And that's correct for a transistor that's turned on. 0.7 volts base to emitter. The transistor's turned on. What's on the collector? 20 volts. Well, if there's 20 volts on the collector, it can't be turned on. The fact there's 20 volts either end of this resistor, 20 volts, means that there's absolutely zero current flowing that way. If there was any current flowing that way, there'd be a voltage drop. So there's no current flowing down through the transistor collector to emitter. We've got base emitter current, but not collector emitter current. And it's turned on, and we should have, and we ain't. So the only explanation for this, really, is that it's open circuit here, base to collector. We know it's okay base to emitter because we have the 0.7 drop. We know this resistor's okay because you've got 3.3 across it, yeah, making up to the 4. 16 plus 3, 0.7 plus 3.3 is 20. It all adds up, yeah? So we know certainly this transistor is faulty. And the problem with it is it's open circuit, yeah? It's open circuit, base to collector, or collector to base, yeah, whichever. That's what's wrong with that circuit. That's using Ohm's law to work out the voltage divider and understanding when this transistor's turned on, the voltage here should be very low. So I hope you got that one right. Let's do another one. We'll have one more. We won't do. I won't challenge you guys too much on this. Let's just do one more, yeah. So what we've got in this one, 20 volts input again, yeah. Got resistor, transistor, yeah. Another resistor, 0 volts, yeah. It's an NPN transistor again, okay. Coming into here, we have a resistor from the 20 volts, and we have a capacitor in, out, yeah. That's what we have. This is a 250k resistor, yeah. This is a 2k resistor, okay. And we measure the voltages again. So we measure the voltage first across this resistor, yeah. We can measure. Let's measure the voltage from here to here, yeah. And what have we got? We get 19.85 volts from there to there, yeah. We've measured that. Now let's measure the voltage from the emitter to ground, the voltage across this resistor, yeah. So we're going to connect a meter probe to here, red, black. We're going to measure this here, yeah. And we find we got 0.15 volts. And there we got 19.85. Okay. Let's measure the voltage on the output. Okay. So again, we'll connect our test meter to here and to here, red, black, and we've got 20 volts. Is the circuit working? Is it working? Is it reasonable that we have 20 volts on here, 19.85 and 0.15? Well, the first thing we can say, again, there's no voltage drop across this resistor, therefore there's no current flowing. So there's no current flowing that way to the collector emitter to ground, through this resistor. There's no current flow this way, yeah? Because there's no voltage drop across the resistor. So the transistor is turned off. Yeah? What's the voltage here? Well, we've measured from this resistor to here, and we know it's 19.85, yeah? And the total voltage supplied was 20. So the remaining 0.15, where is it? Well, it's across this resistor. So what's the voltage from the emitter to the base? Well, we can measure it, or we can work it out. Yeah. Let's work it out. 19.85 plus 0.15 equals 20. Therefore, this would be 0. Let's measure it. It's 0 volts. There's 0 volts from the base to emitter. So this transistor is turned off. There's no forward bias, yeah? No bias, it's turned off. So that's reasonable that we would have 20 volts on here, because if there's no current coming through here, there's no current coming through there. Yeah? That's it. That would seem reasonable, yeah? But is it? Because look, we've got a voltage drop across here of 0.15. And we've got a voltage drop across here of 19.85. And the only reason we can have a voltage drop across here is if current is flowing from this resistor, through the base emitter, and through this resistor. If there was no current flowing, we wouldn't have a voltage drop here, and we do have. Now let's look at the two values of these resistors. These are forming a resistor voltage divider. We've got 250, yeah, and we've got 2k. And the base emitter is in between, yeah. So in between this is the base to emitter, yeah. Make it look better for you. Okay, right. So the total resistance, this is 20, this is 0 volts. The total resistance, the two together, is 252k. So what should be the voltage drop across this resistor, if that's the case? Which is quite easy to work out, actually. This is Ohm's law. You take 20 volts, yeah, and you divide it by the total resistance, yeah, 252,000, yeah, and then you multiply it by the resistance of the one you want to know the voltage drop across, yeah, times 250,000. If you wanted to know the voltage across this one, you take 20 volts, yeah, divided by 252,000, yeah, times 2,000. So I can't do that in my head. I can do it roughly in my head, if that was 200. I can do it very close in my head, actually. Taught us mental arithmetic at school, you know, I can do it very close in my head there. But let's get a calculator, as is the modern way, and let's have a look to see what we have, yeah? So let's go over to the screen capture, right. So let's get the calculator. So the total resistance, so the voltage was 20 volts, yeah? And we're going to divide it by the total resistance, 252,000, yeah? Equals some very small number. Then we're going to multiply it by the big resistor times 250,000, times 250,000, yeah? And we get 19.84, isn't it? 19.84. And if we multiply, let's do the other one, but we can see obviously what it's going to be. It's going to be about 0.15. But let's do it anyway, just to be sure. So we have 252,000. Sorry, clear that. Get ahead of myself. We have 20 volts divided by 252,000, yeah, times 2,000, the little resistor. 0.158. So that's what we've got. That's what the voltages are, yeah? Let's go back to the desktop again. There we go. So that mathematics just proved that we'd have 0.84 volts here and 0.15 volts here, yeah? Which is exactly what we read in here. 0.85, it's close enough, yeah? So the resistance of the transistor, base to emitter, must be 0, yeah? So effectively you've got 250k, yeah? You've got base to emitter, and you've got 2k, yeah? 0 volts, 20 volts, and because we've got 19.85 here and 0.15 here, yeah, the resistance of this is 0. That's a short circuit. So this circuit isn't working, it's faulty, and it's short base to emitter without using a resistance meter. You'll say, what's the point? Well, the point is just to prove you understood it properly, yeah? Get your meter out and get on the resistance or diode range and go find the short circuit. Okay guys, hope you like that, and hope you enjoyed that. One other thing I will mention before I go, and I will go after this. If we were doing all this with PNP transistors, it's the same. All these voltages are the same. It's just negative. It's back to front, yeah? So like your base emitter is minus 0.7 on the PNP compared to the emitter, yeah? Because people's brains, mine, and probably a lot of others, don't work well in negative voltages. If you're testing PNP transistors, reverse your meter leads, yeah? Put the red lead onto ground and use your black one to probe. Put them the other way around. You'll now read positive voltages just the same you would on an NPN transistor, and you'll find it works a lot clearer in your head. You can still picture what's going on, yeah? Rather than having all these minuses. Do that. Connect your meter the other way around. Okay, so that's the end of that one. Sorry it was a little bit long. I did want to get through a lot of information there. I hope you really feel confident now about working on bipolar transistors. And now you've got that confidence, I'm going to tell you, you're probably not going to see that many of them. Bipolar transistors are old technology, yeah? They were replaced really with MOSFETs. MOSFETs are transistors, the metal oxide semiconductors field effect transistors. Yeah, metal oxide semiconductor field effect transistor. MOSFETs are transistors, but they work in a different way. And when it comes down to testing them, it's different, yeah? So you will see MOSFETs much more often. Unless you're working on amplifiers, maybe more vintage equipment, you'll see bipolar transistors. You see them elsewhere, you do find them. So now you're going to need to know about MOSFETs, aren't you? And that's the topic of the next beginner's lesson. So I'll see you soon on that one. Have a good day now. Cheers, guys.